An object falls from here to here over a distance h starting from rest, or zero velocity. The question is, how fast is it travelling after falling that distance h? We'll do this in two ways. They'll give the same answer. Well, so why do it twice? One reason is to show that there is often more than one way to treat a problem in science, and the second is that it will help us see how work done provides a link between a forces approach and an energy approach. So firstly, the forces approach. Remember, we're trying to find v after falling a distance h. In the absence of drag, the only force on the object is its weight, mg. Because it's the only force, we don't need to add any forces together to find the resultant, and so the resultant force is also mg. Newton's second law tells us that the resultant force is equal to the mass times acceleration, and so we end up with the result that the object accelerates at g, the acceleration due to gravity. We should have expected this really, because that's what g is. Now we know the acceleration, we can find how much time it takes to travel the distance h, and then how much speed it has gained in that time. So here goes. The distance travelled, h, is equal to the average speed multiplied by the time taken, and we'll call this time t. Because the acceleration is uniform, the average speed will occur at time t over 2, and will be half the final speed v, that is, v over 2. By the way, the average speed occurs halfway through the time interval, but less than halfway through the distance travelled, because of the increase in speed throughout the journey. Distance equals average speed times time becomes h for distance equals v over 2 for average speed times t, and rearranging gives t in terms of h and v. Now we can use the fact that for uniform acceleration, the speed gained is the acceleration multiplied by the time that it occurs for. We can substitute in for t so that we have the velocity gain as a function of distance rather than of time. And since it started from rest, the object's velocity gain is equal to its final velocity v. So finally, by collecting the v's together and square rooting, we have the result that v equals root 2gh. This is a useful result because having a general functional relationship between v and h means that we can find how fast it is travelling after any distance fallen. Next, the energy approach. The gravitational potential energy of an object, a distance h above a reference height, is given by E equals mgh. When the object falls through the distance h, that gravitational potential energy turns into kinetic energy, the energy of movement. That kinetic energy is given by half mv squared, and we can equate that to the loss in gravitational potential energy. Notice that we don't need to consider the time taken for this to happen in this approach. The m's cancel, and we're left with v equals root 2gh, exactly the same as from the forces approach. Finally, notice that there is a connection between forces and energies. The equation gravitational potential energy equals mgh did not arrive by magic. It is the work done on the object by the Earth's gravitational field. That work done is the force due to gravity, mg, multiplied by the distance travelled, h. Its result is to increase the kinetic energy of the object by that amount.